The topic I'm going to talk is about 3D seismic image processing for unconformities. Before talking about our work, let me first show you a delicious image here. So this image looks delicious. You can see that gas and oil are sandwiched by two impermeable layers on both the left and the right hand side, and then covered by an unconformity on the top. So this image provides a very good reason why we want to work on the unconformities, because sometimes if we can detect the unconformities, then we may find oil or gas below or above the unconformities. So there is a 2D real seismic image with two unconformities. But if you cannot recognize these two unconformities, then you may want to use our method to compute unconformity negative image, which is overlapped on the seismic image, to highlight out the positions of the unconformities. So in this unconformity negative image, the large values denoted by the red color indicate the positions of the unconformities. And the ridges of this unconformity negative image shown here provide more resolvable positions of the two unconformities in the seismic image. And we call these ridges thin unconformity negative image. So here in this example, we detect these unconformities are actually not because of oil and gas. We actually have two different reasons for doing that. The first one is that, just as Anias discussed yesterday, for such a seismic image with unconformities, the conventional structural tensor method cannot accurately estimate the seismic load vectors at the unconformities. So the seismic reflect structures below and above the unconformities are different, which means that the seismic load vectors should be discontinuous at the unconformities. However, the seismic load vectors estimated by using the conventional structural tensor method shown here are smooth at the unconformities. Here the image above is the vertical component of the seismic load vectors, and the image below is the horizontal component of the estimated seismic load vectors. So we've observed that both of these two components are smooth at the unconformities, therefore they're not accurate. But now we have detect these unconformities by using the unconformity negatives. Therefore, we can use this unconformity negative as constraints to more accurately estimate the seismic load vectors, as shown here. We observe that these seismic load vectors are discontinuous at the unconformities as we expect. So the second reason for detecting the unconformity is that the flattening method we discussed yesterday cannot correctly flatten the seismic image with unconformities, as shown in this image. So but again, we have detected the unconformities by using the unconformity negative. Then we can use this unconformity negative as constraints to more accurately flatten the seismic image with unconformities. So therefore, in this presentation, we will have three different parts. The first part is how to compute the unconformity negatives to highlight the unconformities from the seismic image. The second part is to how more accurately estimate the seismic load vectors at the unconformities. And the third part is how to more correctly flatten a seismic image with unconformities. So now let's talk about how to compute unconformity negatives. And before that, let me use a simple Schreier model to explain a little bit more about the unconformities. So from this simple model, the angular unconformity can be easily recognized because the terminations are apparent here. And this angular unconformity can be is usually tracked into its corresponding correlative conformities as denoted by the blue lines here. And these three parts, the angular unconformity and the correlative conformities together, form a complete unconformity as shown here. So we see that these three parts together form a complete unconformity because these three parts together form a boundary which separates the sediments to two different depositional units, which means that the sediments above and below this boundary are deposited in different environments. So if we flatten this model, the unconformity will produce a vertical gap in this flattened image because an unconformity represents a deposition break. So now let me use this synthetic image to explain how to compute the unconformity magnitude. And so this image shown here has a complete unconformity with both the angular unconformity and the correlative conformity. So here I want to comment that most unconformity detection method can only detect the angular unconformity. However, our unconformity magnitudes can detect both the angular unconformity and its corresponding correlative conformity. So to compute this unconformity magnitudes, we define two different struct tensors, TC and TA. So a struct tensor is computed by smoothing each component of the outer product of the image gradients. And here the struct tensor TC is computed by first applying a vertical causal smoothing filter to each component of the outer product, and then applying a struct-oriented smoothing filter to each component. A struct-oriented filter is a smoothing filter that smoothes non-structures. For example, in a seismic image, such a struct-oriented smoothing filter smoothes along the seismic reflectors. And here the struct tensor TA is computed by first applying a vertical anti-causal smoothing filter to each component and then applying a struct-oriented smoothing filter to each component. So now let me use this image F to explain how to compute these two different struct tensors, TC and TA. Firstly, we compute the image gradient G, which is of course a vector. And the vertical component of this vector G is, as shown above, is the vertical derivative of the image F. And the horizontal component of this vector G, as shown below, is the horizontal derivation of the image F. So using this image gradient G, we compute the out product G times G transpose. So in this out product, there are 4 components, but only 3 of them are distinct. So the first component is G times G as shown above, and the second component is Z times Gx as shown in the middle. And the third component is Jx times Jx as shown below. So then we are applying a vertical causal smoothing filter to each component of this out product. We observe that after applying this vertical causal smoothing filter, the structures in these 3 images are smoothed from above to below. But if we are applying a vertical anti-causal smoothing filter, then the structures in these 3 images will smooth from below to above. So now for the smoothed outer product with the vertical causal smoothing filter, we further applying a struct-oriented smoothing filter. And after doing that, the structures in these 3 images are extended along the seismic reflectors. And this smooth out product is the struct tensor TC. So now for the struct tensor TA, we first apply the vertical anti-causal smoothing filter to each component, and then applying a vertical applying a struct-oriented smoothing filter to each of these components. And this smooth out product is the struct tensor TA. So now we have there's 2 struct tensors TA and TC. Then we apply the eigen decomposition to the struct tensor TC to compute its corresponding seismic normal vectors you see as denoted by the red segments in the image above. And the two images below are the vertical and the horizontal component of this normal vector field. Then we also do the eigen decomposition to the structure tensor TA to obtain the corresponding seismic lower vectors UA as denoted by the blue segments in the image above. So, and again, the two images below are the vertical and the horizontal component of this vector field UA. So now if we observe these two vector fields, we can see that the two components of UA are shifted above compared to the two components of the vector field you see. So now let's look closer to the differences between these two vector fields UC and UA. Again, this red segment shown here represent the seismic lower vectors UC. Comparing to the seismic lower vector UA denoted by the blue segments, we can observe that these two different vectors are only different at the unconformity. Therefore, an attribute that evaluates the difference between these two vector fields can be used to detect the unconformity. And our unconformity likelihood is such an attribute. So we compute this unconformity likelihood by 1 minus the dot product of vector UC and the UA. Here, these two vectors UC and UA are unit vectors. And we assume that the angle between these two vectors cannot be bigger than 90 degrees. Then this dot product is just a number between 1 to 0. And this product is smaller when the angle between these two vectors is bigger. Therefore, we use 1 minus this dot product to evaluate the vector differences. And the power P here is a big number that we use to increase the contrast between the samples with small and large vector differences. The thin unconformity likelihood image shown here is an image of the ridges of the previous unconformity likelihood image. And we compute these ridges by simply scanning each color of this unconformity likelihood image, preserving all the local maximums and setting zeros to elsewhere to get this thin unconformity likelihood image. And this image correctly aligns with the true unconformity as shown here. So again, this is the 2D example I showed you before. So from this image, we compute an unconformity likelihood image to highlight of these two unconformities in the seismic image. And this thin unconformity likelihood image correctly coincides with the seismic, the unconformities in this seismic image. So here we discussed our method by using the 2D examples, but our method is really a 3D method, and here is a 3D example for this method. So this 3D seismic image shown here also has two unconformities. And in this 3D case, we expect that the unconformities should be surfaces. So now from this seismic image, we compute an unconformity likelihood image shown here, which highlight out the two unconformities. And here for this image, I would like you to pay attention to the upper left panel, which is the time slice of this unconformity likelihood image. We observe that this time slice is separated into two different parts by the unconformity likelihood. And we observe that the amplitude values on the southwest part are almost uniform, and the amplitude values in the northwest part change fast, which means that these two parts separated by the unconformity likelihood has two different seismic phases. So now this is the thin unconformity likelihood image And again, this thin unconformity magnitude correctly coincides with the unconformities. And for this image, I would like you to pay attention to the image with two colorful surfaces. So here I want to remind you that these two surfaces are not seismic horizon surfaces that I showed you yesterday. They are actually unconformity surfaces we extracted, computed by using this thin unconformity magnitude. So now we have discussed how to compute the unconformity magnitude to detect the unconformities from 3D seismic image or 2D seismic image. So now let's talk about how to use this unconformity magnitude as constraints to more accurately estimate the seismic load vectors at the unconformities. In the conventional structure tensor method for estimating seismic load vectors, the structure tensor is computed by applying a Gaussian smoothing filter to each component of the outer product. So this conventional structure tensor cannot correctly estimate the seismic load vectors at the unconformities because the Gaussian smooth filter here will smooth out the discontinuities at the unconformities. Therefore, to improve the structure tensor method, we use the unconformity magnitude as constraints to compute an improved structure tensor. In this improved structure tensor, each component is smoothed by a spatially variant smoothing filter. In this filter, the smoothing extent is controlled by the unconformity magnitudes, which means that this smoothing filter does not smoothing across the unconformities. Because here we know the positions of the unconformities, then we can turn off the smoothing at the unconformities. So therefore, the discontinuities at the unconformities can be preserved in this improved structure tensor. So now let's apply this two structure tensor method to this synthetic image. And these two images shown here are the vertical and the horizontal component of the seismic load vectors that we estimated by using the conventional structure tensor method, which is not accurate because both of these two components are smooth at the unconformities. So now applying our improved structure tensor method to this synthetic image, the seismic load vectors estimated shown here are discontinuous at the unconformities. And this is what we expect. So if we compare these estimated load vectors to the true seismic load vectors, we can observe that these estimated load vectors are almost the same as the true seismic load vectors. And again, this is the 2D example I showed you before, and these two images are the vertical and the horizontal component of the seismic load vectors we estimate by using the conventional structure tensor method, which are not accurate because they are smooth at the unconformities. And again, using the improved structure tensor method, the seismic load vectors we estimate here are discontinuous at the unconformities. And this is what we expect. So now we can more accurately estimate the seismic load vectors at the unconformities. Then we can use these more accurate seismic load vectors to do a better job for the flattening work. Because recall that to flatten a seismic image, we use the seismic load vectors. So now let's go to our final part, which is how to flatten a seismic image with unconformities. So recall that to flatten a seismic image, we first to solve these two equations to get the vertical shift S, and then use this vertical shift S to compute a relative geologic time image, and then use the relative geologic time image to flatten its corresponding seismic image. But here we use this unconformity magnitude to weight the flattening equations as shown here. And in this weighted flattening method, the weight W has small values at the unconformities and big values elsewhere. So now let's do a kind of a comparison of this weighted and unweighted flattened method by using this 2D seismic image. So for the unweighted flattened method, we use the inaccurate seismic node vectors that are estimated by using the conventional structured tensor method. And this image shown here is the relative geological time image we computed by using the unweighted flattened method. We observe that the geological time values are smooth at the unconformities. So now for using this relative geological time image, the seismic image cannot be correctly flattened at the unconformities, because at the unconformities we expect the vertical gaps, again because the unconformities represent the depositional bricks. So now for the weighted flattened method, we use the seismic load vectors that are estimated by using our improved structured tensor method, and then use the unconformity likelihood to weight the flattening equations. So using this weighted flattened method, the relative geological time image we computed is shown here. We can observe that the amplitude values are the relative geological time values are discontinuous at the unconformities. So this is what we want, because again the unconformities represent depositional breaks, which means that the sediments below and above the unconformities should have discontinuous geological times. Again, this is the way computed with the unweighted flattened method. So now using this improved relative geological time image, we can correctly flatten the seismic image. So these two unconformities produce two vertical gaps in this flattened image, and all other reflectors are correctly flattened. So now let me show you a 3D example for the flattening method. And again, we use the unconformity likelihood shown here to weight the flattening method. And the relative geological time value is computed by using this weighted flattening method. We observe that the relative geological time values are discontinuous at the unconformities. And using this relative geological time value, we can flatten this corresponding seismic image. In this flattened image, these two unconformities again produce two vertical gaps, and all the seismic reflectors are flattened comparing to the original seismic image. So let me just finish here, and I will take your questions. Thank you.